Hello everyone. We've seen that light behaves like a wave when it interferes or diffracts, but as a stream of photons when it knocks electrons out of metal. This raised a natural question: if light can act like a particle, could matter act like a wave? In 1924, the French physicist Louis de Broglie proposed that every moving particle has a wave associated with it. He called these matter waves or de Broglie waves, and this idea changed physics forever. De Broglie gave a simple equation to connect particle momentum and wave wavelength, lambda equals h divided by p, or spoken completely, wavelength lambda equals Planck's constant h divided by momentum p. Since momentum p equals mass m times velocity v, we can also write lambda equals h divided by m times v. Planck's constant h equals 6.63 times 10 raised to the power minus 34 joule-second. This relation shows that wave and particle aspects are linked by a single constant, h. For a photon, momentum p equals h times nu divided by c, where nu is frequency and c is the speed of light. Substituting this into the de Broglie relation gives lambda equals h divided by p equals h times c divided by h times nu, which simplifies to lambda equals c divided by nu. This is exactly the usual formula for light wavelength. So de Broglie's hypothesis works for photons too, proving its consistency. Now, since lambda equals h divided by m times v, the larger the mass or speed of a particle, the smaller its wavelength. For everyday objects, this wavelength is so tiny that it cannot be measured, around 10 to the power minus 34 meters. That's why we don't see wave behavior in cars, balls, or people. But for electrons and atoms, the de Broglie wavelength is comparable to atomic sizes, and their wave behavior becomes significant, as seen in electron diffraction experiments. Let's calculate the de Broglie wavelength of an electron moving at 5.4 times 10 to the power 6 meters per second. Mass m equals 9.11 times 10 to the power minus 31 kilogram. Velocity v equals 5.4 times 10 to the power 6 meter per second. Momentum p equals m times v equals open bracket 9.11 times 10 to the power minus 31 close bracket multiplied by open bracket 5.4 times 10 to the power 6 close bracket, giving p equals 4.92 times 10 to the power minus 24 kilogram meter per second. Now lambda equals h divided by p equals open bracket 6.63 times 10 to the power minus 34 close bracket divided by open bracket 4.92 times 10 to the power minus 24 close bracket. That gives lambda equals 1.35 times 10 to the power minus 10 meter, or 0.135 nanometer. This value is comparable to X-ray wavelengths, which is why electrons can produce diffraction patterns similar to light. Now let's try a macroscopic object, a ball of mass 0.15 kg moving at 30 meters per second. Momentum p equals m times v equals 0.15 multiplied by 30 equals 4.5 kg meter per second. So lambda equals h divided by p equals open bracket 6.63 times 10 to the power minus 34 close bracket divided by 4.5. That gives lambda equals 1.47 times 10 to the power minus 34 meter, so tiny that it's practically zero. This is why macroscopic objects never show wave behavior, that de Broglie wavelengths are too small to detect. De Broglie's idea meant that every particle has a wave associated with it. The wave describes the probability of finding the particle in a given region, not a physical vibration in space. This concept was later expanded by Erwin Schrödinger into the famous wave mechanics, which forms the core of quantum theory. So an electron is no longer just a tiny ball orbiting the nucleus, it's a wave spread through space whose square gives the probability of its position. To sum up, Every moving particle of mass m and velocity v has a wavelength given by lambda equals h divided by m times v. This is called the de Broglie wavelength. For microscopic particles like electrons, the wavelength is measurable and shows wave behavior. For macroscopic bodies, the wavelength is so tiny that their motion appears purely particle-like. De Broglie's insight united the worlds of waves and particles, laying the foundation for quantum mechanics and modern physics. Thank you for listening, and see you next time as we explore how these matter waves shape the quantum structure of atoms themselves.